Hello. So, welcome back to the other gate sessions. Last session we were discussing gate 2021 part 2. So, in this session we will be continuing with the 2021. This is a ninth session and third session on the 2021 question paper. So, this was the last question we were discussing with when you apply a magnetic field, the splitting of the uh, spectrum. Okay, so we will move around with the next question. So this is the next question. It's a question from electrostatics. Consider a point charge plus q of mass m suspended by a massless inextensible strength of length L in free space. It is placed at a height d over an infinitely large ground conducting plane. So this plane, this one is grounded. That's what they are saying. And the gravitational potential energy is assumed to be zero at the position of conducting plane. So here actually gravitational potential, you can take h equal to 0 because mgh is the gravitational potential. So here you can assume h is 0 here. Okay, so if theta represents the angular position and p theta is a corresponding canonical momentum, then the correct Hamiltonian of the system. What is the Hamiltonian of the system? So everyone know Hamiltonian is a total energy, will be like kinetic energy plus potential energy. So here this is the only moving component, the charge plus q, which has a mass of m. So and if p theta, the angular, if theta is the angular displacement and the corresponding momentum is p theta, then of course the kinetic energy will be T, will be like p square by p theta square by 2m. Okay, so since it is a angular part, there should be a L square also, because it's a angular. Usually, like when we have a coordinate, theta does not have any dimension, right? If we have x position and the corresponding momenta is px, then it should be, the kinetic energy will be like p square by 2m. So here also, if you like just look at the dimension also, if you think about the dimension matching, so p theta will be like some rate of change of theta in terms of something like that. So there's a dimensional, unless you put a L square, there's a dimensional ambiguity there. So p theta square by 2m L square is the momentum, the angular part of kinetic energy. Now there is only potential energy you have to deal with. So if you look at, there are two potential energies. So one is gravitational potential, which tries to attract this charge towards now. So that will be just simply mgh. Okay, so actually I have drawn here. If it is suspended at a distance d and this string has a length L, then basically this distance is given by L, d minus L cos theta. So they have given that here you have to take height 0. So the height from this point to here is d minus L cos theta. So that will give you a gravitational potential, which is mg d minus L cos theta. Okay, so that's how you get the gravitational potential energy. So all of these options have this mg d minus L cos theta. Okay, so the one thing to note, like since it is going 0 is defined here at the position of the infinite conducting plane. So this is the infinitely conducting plane, grounded plane, and height increases from here. So your potential energy increases as you go upward, right? So in that sense this will not happen. So minus is not the answer, so you are again ended up with either this one or this one. Both of them have the correct kinetic energy, but the angular, the potential energy, now you got the one part which is a gravitational part. Now what else? So you have when you suspend a charge above, say this is plus q, infinitely grounded, infinitely big and grounded conducting plane. So what happens is that if this is plus q, minus charge will be all around this due to the electrostatic attraction from this plus q, that will cause electric field like this, and there will be minus charge all along this towards infinity also. So that will give you like a potential, and in the entire system there is a plus q and there is a minus q distribution of charges is there, so that there is a like electrostatic potential energy in the system. So that also you have to consider. You might have remembered this. You can actually find out the electric field due to this kind of system by applying the method of images. So this is actually equivalent to a plus q charge here. If this distance is d and if this is plus q, you put an identical minus charge here, which is again at the same distance from the conducting plane, but at the opposite side. So there will not be conducting plane. So the idea is that the distance between the two charges will be 2d. So this entire distance is 2d. So the field due to this charge setup and this one, these are both equal by the method of images. So this one is something you already know. It's a dipole electric potential and electric field, whatever you want. So this one is equivalent to this one. Only the point is that in this case, if you have a like electric dipole like this, you have electric field throughout the space. In the entire space you have electric field, and also the wherever you have electric field there is a charge. There is energy also in the fields. But in the case of this kind of system, when you have a charge on one side of a infinitely grounded conducting plane, but you don't have any charge in this region. You only have, because it's a grounded kind of system, there is no, if you look here, you have basically like equal and opposite charges on this side of the thing, and there is no energy actually. There is no field and there is no energy. So if you think in terms of energy, in this setup there is only half of the kind of energy in this system. Actually, if you actually find out the electric field and integrate, you basically the energy density of electric fields is basically epsilon square E square, epsilon naught E square. If you integrate this quantity over all space, you will get the total energy in the fields. So this charge setup will be having only half of the time that you have here. So that's how you get like electric potential energy stored in. If you have like plus and minus q charges, then you know this is the at a distance 2d. So here it is given the distance is it x? This is d. It should be d here. So if you have equal and opposite charges placed at a distance 2d, then this thing basically gives you the potential energy stored in the dipole. This is the dipole energy, potential energy. Basically, charge you have q1, q2. One is plus q and the one is minus q, and at a distance 2d. So this will give you the dipole energy, potential energy. Then half of the time that this will give you the energy of this particular system. So you end up with minus q square by 16 pi epsilon d minus L cos theta. That will be your answer. So here if you look at, you have, so this one is minus actually, because you have a plus q and minus q charge, and the potential energy is having a minus sign. But if you look at, if you compare these two, there is a like half factor difference. There is an additional half factor here. So if you do not consider this additional half factor here, because of the whatever, but the thing I told, like there is only electric field only in the half of the space, that basically give you like an error in the formula. So the true answer is 16 pi epsilon. So you have to take the half factor also. Okay, so this one is the right answer. Option D is the right answer. Okay, so that's about this problem. Basically you use the method of images and get the energy of the system. Okay, so I have just written down here why the half factor is coming up. Moving on to the next problem. This one is again, it's an electrostatic problem. Electric fields in matter actually. So the question is, consider two concentric conducting spherical shells as shown in the figure. The inner shell has a radius a, small a, and carries a charge plus q. The outer shell has a radius b and carries a charge minus q. So minus q and plus q, kind of a dipole kind of setup. But the empty space between them is half filled by hemispherical shell of dielectric having permittivity 1. So here you have the blue shaded region, you have a dielectric of permittivity epsilon 1, and the other side is having a permittivity epsilon 0, because it's filled with air. So basically you have two different media in the cavity. This is a kind of cavity. So the question is, what is electric field at the radius from the center, but it is such that A less than R less than. So within this region, what is electric field? Okay, so the thing you have to apply here is that this rule is basically the boundary condition for electric fields. So if you have two media, so this is medium 1 and this is medium 2, and if you have electric field within passing through both of the medium in the space and space, then boundary conditions basically tells you how the perpendicular components like going like this and the parallel components going like this, these are related, like E1 perpendicular, E2 perpendicular, and E1 parallel and E2 parallel. How these are related, that's what the boundary conditions tells you. So the one of the boundary condition is actually E1 parallel is equals E2 parallel, because you have this relation E curl E is minus dou B by dou t, the Faraday's law, electromagnetic induction. So right of when you change the magnetic field, there is a induced electric field. So that basically gives you, like, if you remember how you derive this boundary condition, you take a infinitesimal kind of a loop going through both of the media, and you basically if this is epsilon, the thickness in this thickness in the perpendicular direction, you take the limit epsilon tends to 0, and if this is L, then basically you apply this rule del cross E in this particular loop, then you will get that E1 parallel equals E2, this rule. Just try to refresh through your electrostatics course. So you also be aware of the other, like perpendicular component will have a discontinuity. So here there is no discontinuity, it's a continuous component, but the perpendicular component actually has a discontinuity. that actually comes from the del dot E equals rho by epsilon, this relation. Okay, so anyway, I am not going to that details. So we have to use this even parallel equals E2 parallel. So in this interface between these two media, as I shown here, so you have medium epsilon 1 here and epsilon 0 here, and you have interface here. So if you consider one fact you have to use is that the electric field will be always kind of radially outwards for this kind of setup, because it's a spherical symmetric charge distribution. So you will have a radially outward electric field. So at this interface, basically even if even is a total electric field in medium 0 epsilon 0 and E2 is that in epsilon 1, then E1 is basically E2 by this condition, because your total electric field is actually radially outward and there is no perpendicular component to the interface. Okay, so that basically means there is no perpendicular component and E1 is equals E2. This fact you have to use. So E1 equals E2. This is the fact you have to use from the boundary condition. Now you use the relations like D is epsilon E, D is a dielectric displacement and epsilon is the permittivity of the media. E will be the electric field. So in air you will have D1 equals epsilon 0 E1, and in other medium you will have D2 equals epsilon 1 E2, because the permittivity are different and your electric fields are same. So that means your electric displacement D should be different. So now just apply this rule like E1 equals C2. That will give you D1 by epsilon 0 D1 by epsilon 0 equals D2 by epsilon 1. That means D2 equals epsilon 1 divided by epsilon 0 D1. You get the relation between D2 and D1. So they are not the same. There is a discontinuity in the dielectric displacement as you go from medium 1 to medium 2. Now you apply this like del dot D equals rho. This is something like del dot E is basically rho by epsilon 0, where rho is the charge density. This will actually give rise to like del dot D equals rho F. So where rho F is the free charge density. So free charge means your actual charge density can be either free charges like free electrons, protons, like that, free charges, or you can also have bound charges, due to like if you bound currents happen because if you take a material and you polarize it in this way. So what will happen at the ends, in this end and this end, you basically have a minus and plus charge. There is a charge separation. So even though the net if you add up all the things, the material as it is does not have any net charge overflow, additional charge in the material, but there is charge displacement. So this kind of charges is called, charge density is called bound charges. So this arise when there is a medium and there is a polarization, net polarization for the medium. Okay, so but what happens is that D only concerns about the free charge density, the dielectric displacement. So you have del dot D equals rho F, or if you apply the volume integral here, the Gauss's theorem, you will get that volume integral D dot ds along the surface, closed surface, will be the total charge in the sphere or in the closed surface. So you just consider like a sphere of radius r having a radius within A and B. Then you apply this rule, this particular rule in that sphere, then what you will get? D1 2 pi epsilon. So you have like the total sphere is basically divided into two. This part has a medium epsilon 0 and this part has a medium epsilon 1. but this surface area is basically, the total surface area is 4 pi r square, so the half of that is 2 pi r square. So you have 2 pi r square times d1 plus d2 times 2 pi r square. It's you substitute using this relation epsilon by epsilon 0, 2 pi r square d1 equals q. That you basically get d1 2 pi r square 1 plus epsilon by epsilon 0 equals q, or you will get d1 equals epsilon q by 2 pi r square. This with this relation. Now using this relation d equals epsilon e, you can basically get E1 equals E2 equals D1 divided by epsilon. That will give you like epsilon q divided by 2 pi r square epsilon 0 plus epsilon. So if you look at the options, okay, so they are asking for the direction also, which we already discussed. Like it will be always radially outward, because you have a plus q out inside. If it was minus q inside, it will be radially inward. There will be a minus sign. So in this particular setup, it will be radially outward with the magnitude q by 2 pi epsilon 0 plus epsilon 1 divided by r square, like this. Okay, so there are also like option with additional half factor. So be aware of like this kind of small variations. Okay, so that's about this problem. I hope you understand. So that's the final answer. So sorry, this should be E, not D. They are asking for the electric field, not the dielectric displacement. Okay. Next. So consider a state. This is a question from quantum mechanics. Described by psi of xt, psi 2 of xt, and psi 4 xt, where psi 2, psi 4 are respectively the second and fourth normalized harmonic oscillator wave functions, and omega is the angular frequency of harmonic oscillator. So the wave function psi of xt at time equals 0 will be orthogonal to psi of xt at what time? That's the question. So you have the initial state psi of xt0 and at what time. So basically you have the harmonic oscillator, so you time evolve the state with e to the power minus iht by h squared, where h will be your harmonic oscillator Hamiltonian. Okay, let's do it anyway. So we have the energy eigenvalues for harmonic oscillator and plus half h squared omega, and given that these are psi 1, psi 2 and psi 4 are the first and the second and fourth eigenstates, right? Wave functions. So that means it's a first excited state, so I am denoting it with 1, and the third excited state I am denoting it with 3. So basically we are denoting it with the value n. So 0, n equal to 0 will be the ground state. That means so your 0 will be ground state. You start from 0 and you will get this. And given, so what given to you, it's psi equals 1 plus 3. So note that this is not a normalized wave function. If you take psi, you will get 2. So in order to normalize, your state should be 1 by root 2 times 1 plus 3. Anyway, that does not matter in this case, at least, because you are not calculating any expiration value or something. You are just looking at the time evolution. But be aware of, in some cases they might have asked, they might be asking about like what is the time evolution of this quantity. Then you have to normalize the state. Okay, now that apply the time evolution, it will be e to the power minus ist by h squared acting on psi. This is a time evolution operator, takes from t equal to 0 to t. So basically it pass through, it's a linear operator, so it acts on 1 and 3, and you know that these are energy eigenstates. So basically if h is acted on 1, you will get n equals 1, so 1 plus 3 by 2 h squared omega 1. So this is an eigenvalue equation, and if x acts on 3, you will get 3 plus 1 by 2 is 7 by 2 h cut omega 3. So basically we are using this relation here, and that will give you e to the power minus I 3 by 2 h cut omega t by h cut. So h cut and h cut will cancel off, and you will have a omega t there, and here you have a e raised to minus I 7 by 2 h cut omega t by h cut. And now what they have asked is that, so this is your time evolved state. At any time this will be your state of the system. Now at what time psi of t will be orthogonal to psi of 0? That's the question. So if two states are orthogonal, you will have this condition like psi phi, they are orthogonal, that should be 0. So this is the orthogonality condition. So just apply that here. So what you will get? So your psi 0 is just 1 plus 3, ket 1 plus ket 3, and your psi t is this. So if you apply take the bra of psi and act it on psi of t, then you will get basically this particular factor e to the power minus I 3 by 2 omega t. H cut is cancelled off here, and you will get a e to the power minus I 7 by 2 t omega t, that also. Okay, now pulling out I e to the power I 3 by 2 omega t. Okay, so now I have taken psi of t, so that's why it can be minus also if you take the other way, like psi of ket psi 0, bra psi 0 and ket psi t. Anyway, it's fine. So basically you pull out the factor and you will get this thing. So this, no way you cannot, this is never 0. You cannot make this 0 because it's cos theta plus I theta in that form. It is always like a modulus 1 kind of number. It's like it's a unit circle. It's always lies in this number, always lies in that circle. Whereas this you can make 0. When if this is minus 1, e to the power I 2 omega t is minus 1, this will be 0. That happens when 2 omega t is, so when this is 2n plus 1 pi. When this hot factor 2i omega t is 2 omega t is 2n plus 1 pi, you get this relation. That means t should be 2n plus 1 pi by 2 omega, or for the first time. So this n you can change from like 1 2 3 0 1 2 3 etc. So n equal, if you put n equal 0, you will get the first time when this happens, that will be pi by 2 omega. So your answer is pi by 2 omega. Okay, so that's it. You just take the time evolution. This is how you take the time evolution. This is your time evolution operator that acts on the eigenstates. You will get only the energy as the factor here in the exponential, and you just take the inner product to get the orthogonal to make it orthogonal. Okay, so next one. So consider a single 1D harmonic oscillator of angular frequency omega in equilibrium at temperature 1 by kb beta. The state of, so basically this means beta is 1 by kbt. The states of the harmonic oscillator are all non-degenerate, having energy. These are the energy eigenstates, which energy values which we already know, with equal probability when n is quantum number. N is a quantum number. The Helmholtz free energy of the oscillator is. Okay, so basically the idea is that you find out the partition function of this. So it's a canonical ensemble. So this is these are given that these are the energy eigenvalues. So you find out the partition function, which is sum over I e to the power minus beta ei. Ei's are the possible energy eigenvalues. So here it will be like sum over I. It's not I, it should be n. Sum over n e to the power minus beta n plus half h cut omega. So n goes from 0 to infinity. It's a infinite sum. So there is a e raised to minus beta. This you might have already done this kind of calculation. It's not a very difficult one. Beta h cut omega by 2, this factor, you pull it out. It does not have any n there, so you can simply pull it out. So then you have sum over n e raised to minus n beta h cut omega. So this is a geometric series actually. A geometric series is like AR square, so on. So if you take the sum up to infinity, if R is less than 1, then the value is it's called a sum. The infinite sum will be A by 1 minus R. So this is like this high school stuff. We all learned this in high schools, so that you are applying here. So your first term is A0. A is your first term. When you put n equal to 0, you will get 1. E raised to 0 is 1. So that's why you have a 1 here, divided by your 1 minus R. R is basically e raised to minus beta h cut omega. Each time you multiply the same terms, so that means 1 minus e raised to minus beta h cut omega. So this is your partition function. Now the question is, what is the Helmholtz free energy of the oscillator? So for that you should be knowing this relation. So Helmholtz energy is related to partition function as minus 1 by beta log z. Log z is a partition function, and you just apply that here. So you get minus 1 by beta log of whatever you found out just before, and that will give you have a product of log of a product. That means log of e raised to minus beta h cut omega is beta h cut omega by 2. So there is a minus sign. That's how we are getting a h cut omega by 2 here. And you have in the second term, you just simply put it like this. There is no more simplification possible. So this is the final answer. Let's see. This is the option. So all of the options have this. Yeah, these are the options. And there is one plus here, and there is a minus sign here. So this is only right answer. Option B is the right answer. Okay, so that's it. So next one. A system of two atoms can be in three quantum states having energies 0 epsilon and 2 epsilon. The system is in equilibrium at temperature T equals, again the beta equals 1 by kBt. Match the following statistics with the partition function. Okay, so you are given with, like, there are 4 types of particles, and they are all like only possible energy states are 0 epsilon and 2 epsilon, and there are two particles, 2 atoms. So question is, what if they are classically distinguishable particles, classically indistinguishable, and Fermi Dirac and there are bosons and there are fermions. So okay, let's do one by one. Just move this. Okay. Classical, what if they are classically distinguishable? So these are the usual particles we observe. In this case, what you have to do is basically you find out the partition function for one particle, and since they are not interacting, these are non-interacting particles. Since it is not given anything like here, these are interacting particles, you can assume that these are non-interacting. So what you can do is just basically like take the, if there are n particles, if Z1 is a single particle partition function, then that raised to n will give you the n particle partition function. Non-interacting, that should be noted. The non-interacting partition function of n particle is basically given by this in the case of classically distinguishable particles. Okay, so what is Z1? So you have, again, partition function is a sum over e raised to minus beta possible energy eigenvalues. So e raised to 0 is 1, and e raised to minus epsilon plus e raised to minus 2 epsilon. So this is your partition function for one particle, and if you square it, you will get basically this. You do the squaring, then you will get that. Yeah, so you get that. You simplify that also. You have a 2 minus 2 epsilon here and minus 2 epsilon here added up, then you will get this 1 plus 2 e raised to minus epsilon plus 3 times e raised to minus 2 epsilon plus 2 e raised to minus 3 epsilon. Actually there is a pattern like minus epsilon and minus 3 epsilon. There is a 2 here, and minus 2 epsilon there is 3, and e raised to, this is e raised to 0, and 0 and e raised to minus 4 epsilon, they are having the factor 1. Okay, so if you go back to the options, you can basically see 1 e raised to minus epsilon. So this one. Okay, so this one correspond to your classically distinguishable particles. Okay, so CD is Z3. Yeah, that's so you're right. This option C is the right answer, which I already worked out. We will go one by one. So CD goes to Z3. And what if the next one? So next easiest one is a Fermi. If they were fermions, what happens? Because you have this constraint, like you cannot put two fermions in the same energy states. You cannot put two fermions in the same state. So possible energies. So I have shown which are the possible energies. There are two particles. No two can be in the same state. So 0 and epsilon is one configuration, and 0 and 2 epsilon is another possibility. And this should be here, epsilon and 2 epsilon. Just make all possible combinations such that they are just no two particles are in the same state. Okay, so one question now you should ask is that, you should be knowing this. There is no fermions are basically indistinguishable. So that means if you just like label them as 1, 2, and if you can also imagine a state like when the 2 is here and 1 is here. So this is not possible because there is no kind of 1, 2 kind of numbering for fermions. They are all identical. If you take any electron, it will be identical to any other electron in this universe. So they are indistinguishable. So there is only this kind of configuration you have to consider. That means your partition function is now basically e raised to minus. These are the only possible energy eigenstates of the combined system. So you have e raised to minus epsilon plus e raised to minus 2 epsilon and e raised to minus 3 epsilon. Let's see. Yeah, so this is fermions. So this will correspond to Fermi Dirac. So FD goes to Z1. Yeah, FD goes to Z1. Now what if they are bosons? Bosons actually can sit in the same state. So 0, 0 is possibility, epsilon, epsilon is a possibility, 2 epsilon, 2 epsilon is a possibility. Again with the states which are possible for fermions, they can be in different states also. So these are also possible. Again here also there is no 1, 2 bosons. Bosons are also indistinguishable. So you cannot permute between them. Maybe this also I can say. Fermions take a asymmetric state, antisymmetric wave function, such that if you just interchange two of them, it will take a minus sign, the wave function, and bosons take a symmetric wave function. So if you interchange two bosons, you will get a +1 eigenvalue. Okay, so that's not part of this question, but I'm just telling. Now, what are the possible energies? Like this will give you 0, 2 epsilon, 4 epsilon, and in addition you have these states. Okay, minus epsilon, epsilon, 2 epsilon, 3 epsilon. So you have two epsilons here that you add up, and you get, if you look back, you will get this minus 4 epsilon, this one. Okay, Z2 is the Bose-Einstein state. Okay, now the last one. What if they are classically indistinguishable? So what's the difference between classically indistinguishable and classically indistinguishable. So if you remember this problem, like in order to the problem, I exactly don't remember the term, but if you in order to make entropy additive, so you have to put an additional n factorial there. So you construct the classically distinguishable partition function of n particles, then you divide it with n factorial to in order to make the entropy. If you, even if you add to, entropy should be additive, so that in order to make that you have to make this additional n factor. So I don't exactly remember the paradox. It's a Gibbs, okay, so Gibbs paradox. So if you just look back, so in order to fix Gibbs paradox, there is an additional 1 by n factorial coming in to construct the classically indistinguishable particle wave partition function. So just put whatever was your indistinguishable partition function, you just have a 1 by 2 with, because you have two particles, so this one will give you classically indistinguishable particles partition function. So that's it. Next we are moving on to the next. Consider a spherical galaxy of total mass m and radius r having a uniform matter distribution. In this idealized situation, the orbital speed v of a star of mass m very much less than capital M, assuming the galaxy as a function of the distance r from the galactic center is best described by Butler. Okay, so basically you have a galaxy like this and you have a planet, or is it a star? Star, yeah, it's a star. This revolves. So if r is the radius of galaxy, and you can consider two orbits, like one is outside and one is inside r. So if you observe the velocity of the star, the speed of revolution of the star around the center of galaxy, what is the trend? That's the question. The one thing you can guess is that if you go outside r, so also given that inside capital R there is a uniform mass distribution. It's a spherical galaxy and there is a uniform mass distribution. So if you go very far away, this will be again, this looks like a point mass. So your total mass will be like 4 by 3 if 4 by 3 pi r cube will be the volume of the galaxy times rho. If rho is a uniform mass density, then this will be the mass of the galaxy centered at the, I mean the, if you go far apart, this will look like a point mass, point particle, point kind of object. So that means that the usual gravitational rules should follow, right? So in the usual, I think I have, in the, if you remember this orbital velocity of any satellite around planet or something, or star, whatever gravitational body, it actually goes like, the relation is 2gm by r. So basically you equate your gravitational force equals your centripetal force. So gm by r square is mv square by r. That will give you the orbital velocity is root 2gm by r, where r is a radius of the orbit. So basically new orbit will goes like 1 by root r. If you increase radius, you will decrease the orbital velocity. So that means it should goes down, but so that means this 2 out of question. So this cannot be the answer. What about B and A now? Whether it will be like increasing or it's a constant. How to do this? So again a fairly, this is how you can guess. If you consider radius which is less than capital R, so total mass within R is basically R cube. right? Now uh, if you roughly take it as a like on a object, again a point mass at the center, and whatever mass outside this radius, since it is like every object, if you consider, if this is roughly here, then it has like attractive force from all these points. So roughly we can like neglect those effect because it's all the way attracted. Or the effect will be due to this mass inside this sphere, small r. So in this actually you can put like again take the orbital kind of picture, but the thing is that now here the gmm by r, this m, capital M, is basically the mass of the, is a function of r now, because as you increase r, as I told, it's 4 by 3 pi r cube is the radius volume of that the sphere and times your uniform mass distribution. Basically it goes proportional to r cube. That's the idea here, and that should be equals mv square by l, which is your centripetal force. So r cube and r square will cancel off, you will get a r here, and that will tells you a v square will be proportional to r square roughly, and that will tell you v is proportional to r. So it should be a straight line. Again, it cannot be a constant, so that's how it should be option A. One thing also I wanted to just mention here, similar kind of setup comes when you have a uniform charge distribution along a sphere. If you have a sphere which have a uniform charge distribution, and if you look at the electric field at any point, if r is the radius of the sphere, then if you plot your electric field E of r as a function of r, then again you get the same kind of trend. It increases, is proportional to r in this region, and it will go 1 by root r in this. It is actually 1 by r square, not 1 by root r. It kind of increases up to capital R and decreases then on. So this is in the case of a charge distribution, whereas this was in the case of a mass distribution. So I just want to show you the similarity between. It's kind of interesting thing. Okay, now how much time do we have? 40. So 1 or 2% we can. So as shown in the figure, inverse magnetic susceptibility 1 by chi is plotted as a function of temperature for 3 different materials in parametric states. Okay, so Curie temperature of ferromagnetic materials Tc, and Neal temperature of the antiferromagnetic is Tn, and choose the correct answer. Okay, so this is 1 by chi T relation. So the formula you have to remember for this problem is this: chi equals C by T plus Tc. So this you might be already know. The chi is proportional to 1 by T. This is a Curie's law, and similarly that happens for paramagnets. That means Tc equals 0. So I have turned down here Tc equals 0 for para. This is your Curie's law. Similarly, you have other case also. When you have a ferromagnetic object, your Tc should be less than 0 here, and if it's antiferromagnetic, you should have a Tc greater than 0. Okay, now if you look at that, so you are plotting. So when you have this relation, you can actually invert it. 1 by chi will be proportional to T plus Tc, Then if you, and by chi, this is your y axis, and x axis basically t, then tc is basically the y intercept of the straight line. Okay, so that means tc is less than 0, y intercept is negative for a ferromagnetic, so that means 3 is ferro, and tc equals 0, this is for para, and tc is greater than 0, this is for anti-ferro. Okay, now just look at the options. Material 1 is antiferromagnetic, and 2 is paramagnetic, 3 is ferromagnetic, which is true. And in any other things, these are just, again, these are all wrong. That's all. So just remember this relation, like Curie chi is c by t plus tc, and this when it is positive, and this tc is positive, tc is negative. So next one, P and Q are two Hermitian matrices, and there exists a matrix R which diagonalizes both of them, such that RP R inverse equals S1 and RQ R inverse equals S2, where S1 S2 are diagonal matrices. So the correct answer statements are, which are the correct answer. Okay, so given that these are Hermitian, you can write down this P equals P dagger and Q equals Q dagger, and RP R inverse equals 1. This is already given. So these are the given informations. So what about option A? All the elements of both matrices S1 S2 are real, because you know that it's a Hermitian matrix. All the Hermitian matrices should have real eigenvalues, so they cannot have a complex or imaginary eigenvalues. So option A is true. Because these are the diagonal forms, like S1 S2 are the, once you diagonalize P and Q, you will get S1 and S2. So that should be having only the form of them will be like S1 will be some, you have a diagonal entries and 0 here. Similarly S2 also, but all the elements should be real. Eigenvalues are in the diagonal elements of the matrix. So option A is true. Now what about option B? The matrix PQ can have complex eigenvalues, and C, the matrix QP can have complex eigenvalues. Let's try this one, these two together. So PQ all dagger is basically you apply the AB or dagger kind of relation. So Q dagger P dagger, which is P dagger Q dagger, because you actually you use the other relation here. So let's look at option D, then we can come back to B and C. So matrices P and Q commute. So PQ, if PQ is QP, then they commute, right? So we just have to show whether they are equal. So PQ, now put R inverse R and R inverse R here. All these, basically these are invertible matrices, so this is basically identity. You can just put identity anywhere. So that means this is already S1 S2, something you know. Now S1 S2, these are diagonal. So for any diagonal matrix, it is true that S1 S2 is equals S2 S1. This is something you can actually try out. If you take two diagonal matrices, everything else is true. Now if whether you interchange this or this one, your answer is the same. Does not matter whether you multiply this way or this way. You basically multiply the diagonal entries only. There is nothing non-trivial in that. So basically you can interchange them. Now you again put back your R inverse. So this will be Q and this will be P, and that means PQ equals QP. So P and Q commutes. So given that this is true, we can also find out this, like P dagger and Q dagger, they also commute. Now we use this relation here in so that means D is true. Now applying that to B and C, you get basically what they are saying. PQ can have complex eigenvalues and QP can have complex eigenvalues. So Here PQ all dagger is Q dagger P dagger, which is equals P dagger Q dagger, because you have this P and Q, P dagger and Q dagger commutes, which we just obtained now, which is equals PQ, because P is already given that P and Q are Hermitian. So PQ whole dagger is equals PQ, and similarly QP whole dagger equals QP. That means they are themselves like PQ and QP, which are kind of which are the products of two Hermitian matrices. They are also Hermitian. That means any Hermitian matrix can have only real eigenvalues. So this is false. So they cannot have complex eigenvalues. They can have only real eigenvalues. Okay, so just recap. This is the main point you have to remember here. So for any Hermitian matrix, you should be having only real eigenvalues, and what else you be used here. So okay, so any diagonal matrix, if you multiply A with B, when S1 S2 they are diagonal, then it is easy to see that actually S1 equals S2 S1 equals S1 S2. They commute basically. So this is S1 S2. So if S1 S2 are diagonal, so this is something you be used in this, and that means PQ they also commute, and PQ commute means P dagger Q dagger also commute, and using all that we can basically solve this problem. Okay, so next one, do we have time for this? This one takes little time, let me see. Yeah, I think one more problem we can do. So for a two nucleon system in spin singlet state, the spin is represented through Pauli matrices sigma 1, sigma 2 for particles 1 and 2 respectively. The value of sigma 1 dot sigma 2 is what is the value? Okay, so this one actually this little advanced question. So you have to know what is a singlet state. So for any spin half particle, you can basically denote the eigenstate. There are either two possible states, either up or down. So basically I denote with this up and down. Now given this notation, the singlet state is basically up down minus down up. So this is the singlet state. This is called the singlet state. So there is also a triplet state, which is a combination of three states. So you have up and up down plus down up divided by root 2 and down down. So this is called the triplet state, because there are three and this is only one. So a matrix representation of this state is that you can basically this will be your up and up down, down up and down down. So this state will be like, you can write it as this in this matrix form. Now the question, what is expectation value? This is what they are asking, even though it is not very clear. What is the value of sigma 1 sigma dot sigma 2 means what is the expectation value of this operator? So sigma 1 dot sigma 2 is basically sigma 1x sigma 2x plus sigma 2y plus sigma 1z sigma 2. So this Pauli matrices. So basically you sigma 1 x sigma 2 x basically. So this is something you should be knowing. 0 1 1 0 tensor 0 1 1 0. So this is called a tensor product. So basically wherever there is a 1, you put a entire matrix there. So you will get the 0 0 0 1 1 0 like this. So similarly here also you get 0 1 1 0. This is how you calculate the tensor product, and that's what you are getting here. And you similarly do the same for sigma y matrix and sigma z matrix, you will get these, because your sigma y is basically 0 minus I 0, and sigma z is basically 1 0 0 minus 1. So use similar tensor product formulas here also, and you will get these matrices, and you add them up and you will get this. So this is your sigma 1 dot sigma 2. Now just find out the expectation value of singlet state in this operator. So you will get this. Matrix multiplication is only matrix multiplication, so you will get this. At the end you will get a minus 3. So little advanced question, because you have to identify what is singlet state and also this tensor product formalism also. How to take the tensor product of two matrices, Pauli matrices, etc. Okay, anyway, the answer is minus 3. Okay, so I actually have prepared few more questions here. So this will be session 10. Okay, anyway, let me finish this session here. See you all in the next session.